Hello everyone, welcome back to my YouTube channel. As you all know me, I am Aishwarya A, bearing USN number 1V20EC001, currently pursuing 7th semester in the Department of Electronics and Communication Engineering at Sri Venkateshwara College of Engineering. My today's subject is VLSI and the presentation is on operation of MOS transistor and nMOS fabrication. So explanation of operation of MOS transistor in accumulation, depletion and inversion mode. Let us see that the MOS capacitor consists of a metal oxide semiconductor structure as illustrated. Shown is the semiconductor substrate with a thin oxide layer and at the top metal contact referred as the gate. And the second metal layer forms an ohmic contact to the back of the semiconductor and is called bulk contact. The structure as shown as a p-type substrate, we will refer to this as an n-type MOS or nMOS capacitor. To understand the different bias modes of an MOS capacitor, we now consider three different bias voltages, one below the flat band voltage VFB and second between the flat band voltage and the threshold voltage VT, and finally one larger than the threshold voltage. Their bias regimes are called accumulation, depletion, and inversion mode of operation. These three modes as well as the charge distributions associated with each of them. This is the block diagram or a structure for the accumulation, depletion, and inversion mode of a operation, where in accumulation mode Vg is less than Vfb, and in depletion mode Vfb is less than Vg less than Vt, and in the inversion mode Vt is less than Vg. So let us see what happens in all three modes of operation. Now its accumulation occurs typically for a negative voltages where the negative charge on the gate attracts the holes from the substrate to the oxide semiconductor interface. Depletion occurs for the positive voltages. The positive charge on the gate pushes the mobile holes in the substrate. Therefore, the semiconductor is depleted of a mobile carriers at the interface and the negative charge. Due to the ionized acceptor ions is left in the space charge region, the voltage separating the accumulation depletion regime is referred to as a flat band voltage or VFB. Inversion occurs at the voltages beyond the threshold voltage. In the inversion, there exists a negatively charged inversion layer at the semiconductor interface in addition to the depletion layer. Inversion layer is due to the minority carriers and they are attracted to the interface by the positive gate voltage. The energy band diagram of an nMOS capacitor biased in inversion is shown in the figure as I already shown. The oxide is modeled as a semiconductor with a large band gap and blocks any flow of carriers or charges between the semiconductor and the gate metal. The band bending in the semiconductor is consistent with the presence of a depletion layer, and at the semiconductor oxide interface, the Fermi energy is close to the conductor band edge as expected when high density electrons is present. The semiconductor remains in the thermal equilibrium even when the voltage is applied to the gate. The presence of an electric field does not automatically lead to a non-equilibrium condition, as was also the case for a PN diode with the zero bias. Accumulation occurs when one applies a voltage less than the flat band voltage. The negative charge on the gate attracts holes from the substrate to the oxide semiconductor interface. Only a small amount of band bending is needed to build up the accumulation charge so that almost all of the potential variation is within the oxide. Depletion. As a more positive voltage than the flat band voltage is applied, a negative charge builds up in the semiconductor. Initially, this charge is due to the depletion of the semiconductor starting from the oxide semiconductor interface. The depletion layer with further increases with the increasing gate voltage, and this is an inversion operation. As the potential across the semiconductor increases beyond the twice the bulk potential, another type of negative charge emerges at the oxide semiconductor interface. This charge is due to the minority carriers, which form a so-called inversion layer. As one further increases the gate voltage, the depletion layer with barely increases further, since the charge in the inversion layer increases exponentially with the surface potential. Steps involved in nMOS fabrication. Now let us see the nMOS fabrication. Here the first step is oxidation. The process of growing a layer of silicon dioxide on the surface of the silicon wafer is called as an oxidation process. The uses of oxidation process is that it provides isolation between two layers, protect underlying material from contamination. Very thin oxides up from 0 to 100 angstrom are grown usually dry oxidation techniques. Thicker oxides more than 1000 angstrom are grown using wet oxidation techniques. And the second step is that diffusion. Movement of impurity atoms at the surface of the silicon in the bulk silicon from high to lower concentration. Diffusion typically done at the high temperatures, example 800 to 1400 degrees Celsius. The third step is ion implantation. Ion implantation is a process by which impurity ions are accelerated to the high velocity and physically lodged into the target. It is required to activate the impurity atoms and repair physical damage to the crystal lattice. This step is done at 500 to 800 degrees Celsius. Lower temperature process compared to the diffusion can implant through the surface layers. Thus, it is very useful for field threshold adjustment. And unique doping profile is available with the buried concentration peak. Enter image description here. And the fourth step is deposition. Deposition is the means by which various materials are deposited on a silicon wafer or a substrate. The examples are silicon nitrate, silicon dioxide, aluminium, polysilicon. There are various ways to deposit a material on a substrate. These are the ways of deposition. One is chemical vapor deposition, low pressure chemical vapor deposition, plasma enhanced chemical vapor deposition, splatter deposition. Materials deposited using these techniques cover the entire wafer. And the fifth step is etching. Etching is the process of the selectively removing a layer of the metal on the substrate. When etching is performed, the etchant may remove the portions or all of the desired material, underlaying layer or masking layer. The important considerations to be done while doing this step is anisotropy of the etch. It is calculated by A is equals to 1 minus lateral etch rate divided by vertical etch rate. Selectivity of the etch, film to mask and the film to substrate. S-film minus mask is equals to film etch rate by mask etch rate gives the S-film mask. Selectivity of etch. Desired perfect anisotropy A is equals to 1 and infinite selectivity. And the sixth step is photolithography. Components used here are photoresist material, photomask, material to be patterned, positive photoresist. It means areas exposed to the UV light are soluble in the developer. Negative photoresist. Areas not exposed to UV light are soluble in the developer. Steps are apply the photoresist, soft bake, expose to the photoresist to the UV light through the photomask, develop or remove the unwanted photoresist, hard break, etch the exposed layer. Hope my today's presentation was helpful. Thank you for watching my videos. Please like, comment my videos and subscribe to my channel. See you in the next video. Till then, take care. Bye.